Good day, everyone. You are welcome to the last lecture in our series of the STATA training program. So I want to share my screen. I hope you can see my screen.
Yes, ma'am.
Okay, thank you very much. Today we shall be considering logistic regression post-estimation. Logistic regression post-estimation. The first item on the list is the Osman and Lemesho's goodness of fit test. Osman and Lemesho's goodness of fit test. So, in our logistic regression, we have prediction probabilities, and then we have the observed frequencies. So the idea behind the Osman and Lemesho's goodness of fit test is to ensure that the predicted frequency and the observed frequency match as closely as possible. So how do we know whether we have a good fit? A large p-value, as measured by the Osman and Lemesho's test, will indicate a good fit. So now I'm in slide 4. So for our example, please copy that link. Copy and paste, use https/ into the command window of our STATA. Copy and paste into the command window. Make sure you are online. Make sure you are online. Copy that link and paste into the command window, then enter. If you check, I hope you have done that, please. Can I continue?
Please, we've not done that yet.
Okay, please.
Hold on.
Slide 4. Slide 4. Copy that link and paste into the command window. Please ensure you are online.
Which link? There are several links.
Which of the link, ma?
The one that starts with use.
Okay.
Slide 4. Please copy from that use.
To
clear. Clear. Yes, and paste into the command window. And click enter.
Okay.
Have you done that?
Yes, ma.
So have you been able to
Yes, ma.
get the data?
Yes, ma.
Yes, ma.
Okay. So that means I can continue. If we look at that data set, we will see that there are 20 variables. There are 1,200 observations. Of interest to us is this fourth one, high quality. You can see the label high quality school, high versus not. You see the not high is 0, while the high is 1. We also have interest in some other variables like year-round, school, meals, etc. So now that we have our data set, let us generate ym is equal to year-round multiplied by meals. So if we check that, you see that has been added to a number of variables. We now have 21 variables. Okay. So if you have done that, the next thing is to run our regression, logistic regression. We are using logit. You know, the topic says logistic regression post-estimation. So the baseline is that we should first of all have our estimation, maybe logit or logistic. After that, we now proceed to our post-estimation techniques. So the first thing to do is to get the estimation, which is what we want to do now. So the next command is logit at I equal, followed by year-round, followed by meals, followed by full credence forever page underscore ML, then followed by the one we generated, that's ym. Then press enter. So we have our results. I hope you have been able to do that. Have you been able to do that?
Yes, ma.
No, ma, we're not done.
Okay.
Yes, ma.
Okay, so now that we have the results, let us now go to statistics from our menu. Go to statistics. From statistics, go to binary outcomes. From binary outcomes, go to post estimation. From post estimation, go to goodness of fit after logistic /logit /probit. From statistics, go to binary outcomes. From binary outcomes, go to post estimation. From post estimation, go to goodness of fit after logistic /logit /probit. So if you do that successfully, you see that a new window will pop up, and then you see start post estimation tools for logic. You see main, if /in, then wait. Then under that main now, under main, you see report and statistics subcommand. So the first one is report various summary stats and so on and so forth. But the second one is the one we have interest in. So click that second one. Pearson or Osman-Lemeshow goodness of fit test. Click that second one. Pearson or Osman-Lemeshow goodness of fit test. Once you click that, go to the next section, that's test. Under test, click Osman-Lemeshow goodness of fit. Under test, click Osman-Lemeshow goodness of fit. Then the next section, you see test sample. We are using estimation sample first. You can also use all observations in the data, but let's use estimation sample first. So after that, we submit.
Excuse me, ma. What is the estimation sample? Is it the one we estimated already?
Yes, the one we estimated, the one we
Okay.
have from our estimation.
Okay, ma. Thank you, ma.
So
Okay,
once
ma,
you click,
sorry, you said we should use the estimation sample instead of the all observation.
you can also use the all observations. If you check our commands, you see that that one is also included. You get the same results.
Okay.
So if we use that first one, you see instat.gov, group 10 as our command. And then you see the second to the last line, Osman-Lemeshow chi-square 8 is equal to 9.15. Then probability greater than chi-square is 0.3296, which is large. If you compare it to your maybe 0.05 or 0.05 or whatever you are using as your alpha. So it's large. So the larger the p-value, the better the fit. So now that we have a large p-value from this Osman-Lemeshow test, so we conclude that the model has a good fit. The model has a good fit. So if we go back to that window, if you say we should check that box, display table of groups used for test. The last one, display table of groups used for test. Display table of groups used for test. Please check that box. Once you click it, submit. You know, the other time we said that the predicted frequency and the observed frequency, we should ensure that they are as close as possible to each other. So if we have that table, we'll be able to see. So you can see the observed for 1. You can see the expected for 1. You can also see the observed for 0. You can also see the expected for 0. You can look at them, you see that they are very close. So we have a very good fit for our model. Do you have any question on Osman-Lemeshow's goodness of fit test? Any question, please?
Hello, ma'am.
Hello?
On the conclusion to be drawn
Yes.
from the Osman Lemeshow test, is it the probability of chi-square we look at or the Lemeshow value?
The p-value.
You look at probability greater than chi-square. That is 0.3296 in this case.
Are we concluding because it is greater than 0.05?
Yes, that's what we are using. You may decide to use another 1.01 or whatever. Just set your alpha. Based on that, you can always decide.
So that means the null hypothesis is that there's goodness of fit.
The
Null hypothesis will be that there is goodness of fit.
That the model, we are trying to check whether the model has a good fit. So at the end of the day, now what we are saying is that we are accepting that the model has a good fit.
I'm trying to bring out the null hypothesis.
That is what I'm saying. We are accepting the null hypothesis that the model has a good fit.
Thank you.
Okay, so let's now move to the second item. The second item is classification table. In what we have been dealing with is the binary logistic regression. The outcome, they are binary 0 and 1. So what we are trying to do when we fit our model, when we fit our logistic regression model, we have our prediction probabilities. This classification table wants to let us know how far we have gone or how we have fared as far as the modeling is concerned. As in, we have our observations, those that have been assigned to 1 and those that are assigned to 0. We have those observations, and now we have used our model to predict. So we now want to find out what we have been able to obtain based on our predictions. That have we been able to correctly predict those placements, as in those that are supposed to be placed under 1, have they been correctly placed under 1? Those that are supposed to be placed under 0, have they been correctly placed under 0 based on our model? So that is what this classification table will help us to achieve. So after our estimation now, what we do is to run this test, and then we'll be able to bring out some things that will help us know how we have fared as far as the modeling is concerned. So we have some definitions that can help us in our interpretation. So in the first one is cutoff. Cutoff is the threshold value for determining whether an observation has a predicted positive outcome. So STATA has set the threshold 0.5. So that is what we are using. You may decide to change your threshold, but for this training, we are sticking to the default. That is 0.5. So an observation is classified as positive if its predicted probability is greater than or equal to that cutoff, that threshold, that 0.5. So most times we denote that 0.5 by C. So you can see C there. So that is the cutoff. So if an observation is classified as positive if its predicted probability is greater than or equal to 0.5. Otherwise, the observation will be classified as negative. So another thing we have to note is that the classification from our modeling now is correct if it is positive and our Yj is equal to 1 or is present. You know, if you say 1, it means it's present. If you say 0, it means it's absent. Or if it is negative and that observation is 0. So to have a better understanding of this classification concept,
now please, can you? Sorry, ma.
Yes.
Can you maybe show us the slide or so, because we are not following anything.
I thought you had the slides with you. So anyway, for the slides, this is where we are now. So I've tried to give some definitions here, but I want to explain in a clearer form by using this table to illustrate. If you look at this table, you will see that there are two columns, disease and non-disease. This disease means disease is present. The non-disease means disease is absent. The truth means you are talking about the real observations that you have. So those that have disease, you know them. Those that do not have disease, you also know them. What type of disease? Maybe malaria. You now decide to send all of them to the laboratory for test, a particular malaria test. When you send all of them for test, the test results will come out. When test results come out, if those who have the disease also have positive test results, then you say you are true positive. You are true positive. That is, cell A contains true positives, subject with the disease and positive test results. Those patients, they have the disease, they went for the test, and the result came out positive. If you look at cell D, you have true negative there. It means subjects do not have the disease. And the test also say they do not have the disease. Negative, true negative. If you look at cell B, false positive. This one identifies individuals with no disease, but the test result is saying that they have disease. Originally they don't have any disease, but when they went for the test is positive. That is false positive. Look at cell C. Cell C has false negative. What is false negative? You have false negative when you have that negative test result. When the disease that it has been tested for is actually present. Disease is present, but test is saying it is not present. That is false negative. So what are we looking at? You have your true states, those that have the disease and those that do not have the disease. And you have the classification based on test results. Those who have positive test results and those who have negative test results. So if we return to our training now, what we are saying is we have our true observations. Those that you can say they are present and those you can say they are absent. And then we have our classifications based on our model. Those that have been classified as positive and those that have been classified as negative. Do you understand, please? So that is what we want to do. So if we go to slide 12 now, we will just move. We are using the same data set. So from the menu now, you go to statistics. From statistics, go to binary outcome. Go to binary outcomes. From binary outcome, go to post estimation. From post estimation, go to classification statistics after logistic. So it's actually even the first one in the other table, in the other window that we opened the other time. So report various summary statistics, including the classification table. That is the first one. I hope you'll be able to open that window. Have you been able to open that window?
Yes.
Yes.
Okay. Thank you very much. So on that, you click that first option, report various summary statistics, including the classification table. So under test sample, you see use estimation sample. Click that one. You can also use all the others, but let's use the first one. The next section, you see the threshold, positive outcome threshold. Default is 0.5. So you submit. So if you submit now, you can see the table. Just like what you first of all, you see the command. start classification. You see the command start classification. After that, you see that classification table. You can see true, classified. Then you see D, then the other type. If you check the interpretation, you see classified positive. If predicted, that's probability for D is greater than 0.5, greater or equal to 0.5. Then true D, defined as not equal to 0. True D, defined as equal, not equal to 0. So that means that our true D is our positive. The other one is the other side. That is not of high quality. You know, the other time we're trying to look at that icon. We're trying to look at that icon, our data editor. If you go to that data editor window,
we are completely lost, ma.
You are completely lost. Where?
Yes, ma. From the table, ma.
From where?
After the command extract classification. Okay, yes. We are trying to interpret. We are trying to interpret the table now. Please, ma. I want to follow you.
Yes. That is what I'm doing. So we are starting from the table. You can see that table. True. You see D. If you look below, beneath that table, you will see classified positive. If predicted, that quality of D is greater or equal to 0.5. So you can see classified, plus, minus. You can also see true, D and not D. And they are now telling you that true D defined as equal, not equal to 0. Equal, not equal to 0. So if it is not equal to 0, it will be equal to 1. Let's check our data editor. If we check our data editor, look at that variable equal. Are you there?
Yes,
that variable equal. So if you check that, you can see that you have two variables there, not high and high.
Yes, ma'am.
If you check that not high is 0 and high is 1.
Yes,
not high is 0 and high is 1. So it means that from that table, true D defined as equal not equal to 0, it means that this D is the 1 or the plus, and the other one is the negative or the 0.
Okay.
I want you to relate this particular table to the other one that I used for illustration. You know the one that I used for illustration, we have cell A, B, C, and D. And then we had the one we used for illustration. We had cells A, B, C, and D.
Yes.
So now we want to interpret. If you look at this now, you will see that they said sensitivity. Probability positive, given that it is of high quality. That D means high quality because it's from 1. So what is sensitivity? That is the next question. What is sensitivity? Sensitivity is the fraction of observed high quality schools. Well, if we relate it to this particular example, observed high quality schools that have been correctly classified. Please underline that observed. Sensitivity is the fraction of observed high quality schools that have been correctly classified. So when we say observe, we should underline. That means that observe now, for as far as this table is concerned, we will get the observe from the true, those two columns, high quality and not high quality. That D is for high quality, 1. Not high quality is the other one. That is the 0. So now, observe high quality schools. Where will you get observe high quality schools? The first column. That is the first column. So it said observe high quality schools that have been correctly classified. Correctly classified, we give you that positive, given that it is that D. And that is 103, because we are dealing with that column. 103 over 103 plus 35. That is what it will be, times 100. That is what will give us that 74.64%. Sensitivity is the fraction of observed high quality schools that have been correctly classified. So in terms of interpretation now, say the sensitivity is 74.64%. It means that the fraction of observed high quality schools which have been correctly classified is what? 74.64%. Our model has been able to correctly classify 74.64% of high quality schools. That is the interpretation of that sensitivity. The next one is specificity. What is specificity? It is the fraction of observed. Again, the first one is observed, but high quality. That is 1. The second one is also observed, but not high quality. That is the second part. That is the 0 part, not high quality. Observed, not high quality schools that have also been correctly classified. So what is the difference? The difference is the first one is observed high quality sensitivity. The second one is observed not high quality that have also been correctly classified. So specificity is the fraction of observed not high. The other one, that is 0. Quality schools that have been correctly classified. So which ones now? This is the column for not high quality. Column not high quality is this one here. So
yes,
those that have been correctly classified here is this 536. You can see it is this 536. If you follow the illustration that I gave the other time, that you have cell A, true positive, you have cell B false positive, you have cell C false negative, you have cell D true negative.
true negative.
The ones that are true in this illustration, you have cell A and cell D to be true. Cell A and cell D are true. Cell B is not okay. Cell C is also not okay. So that is the one. And so for this specificity, you will see that the one that is correctly classified there will be this 536. And you are dealing with that column over 536 plus 33 times 100. So if you want to interpret this one now, you tell us that those that have been correctly classified under the non-high quality school is 94.20%. Our model has been able to correctly classify 94.20% of the not high quality schools. That is what specificity means as far as interpretation is concerned. The next one is the positive predictive value.
Excuse me, ma.
The positive.
Hello,
Yes?
ma. How do we now
Hello?
relate the percentage to the numbers in the table above? Does it mean
That is
that
what
for
we are saying.
sensitivity, for example, if sensitivity is 74.64% of the high, high, then does it mean that the remaining percentage would be for? I don't understand.
No, just follow what we are saying. Percentage, the fraction of observed high quality schools that have been correctly predicted, correctly classified by our model, is that 103.
Okay.
And the total, as far as observation is concerned, those that have been observed, as far as this one is concerned, is 103 and 35.
Okay.
For high quality, 103 and 35. So what is the fraction that have been correctly classified? It's going out to be 103 over, what is the sum of that column? 138 times 100. That is what is giving us that result. So if you go to the other side, the not high quality schools. So which one have been correctly classified is 536 over the total number of observations. So that means you're talking about the total number in that column. So you have 536 over 569 times 100. We give you that percentage. That is for specificity. So the next one is positive predictive value. What is positive predictive value? It is the proportion of schools with positive classifications that are correctly classified. You know, we said our classifications, they are like the test results. Our classifications are like our test results. So they are on the rows. The observations are on the columns. The classifications are on the rows. So the classifications are on the rows. So positive predictive value is the proportion of schools with positive classifications. Those with positive classifications. So look for the first row. Look for the first row with positive. You can see 103. You can also see 33. And you can see the total, 136. So positive predictive value is the proportion of schools with positive classifications. Positive classification that are correctly classified. If you look at that positive, on that first row, you have all the positives. The A is the one that is the true positive. The A is the true positive. The second one is false positive. The second one, that B, is false. It's not a true positive. So now you need that proportion that is true. The proportion that is true as far as that result is concerned. So proportion of schools with positive classification that are correctly classified. So that will be that A, that is 103 over, what is the total for this row? 103 plus 33, that is 136 times 100. That is what is giving us this 75.74. So positive predictive value, you go row wise, go look for the positives. The positive there is, if you are talking about proportion of schools with positive classifications, all the schools that have positive classifications, now take the ones that have been correctly classified out of all those schools with positive. All the schools that have been, the model has classified are positive, not all of them are true. Just take the proportion of those that are true. And the proportion of those that are true can only be found in cell A. That is why it is 103 plus 33 times 100. That is the 75.74. The next one is the negative predictive value.
So you said times 100. 100 is not
103. 103 yes. Divided by A plus B. Divided by cell A, what you have in cell A plus what you have in cell B. That is 103 divided by 103 plus 33. That is 136. The total for the row, the total for that row is 136 for positive. So 103 divided by 136 times 100% will give us 75.74%. So that is the proportion we are dealing with. So the next one is the negative predictive value. Again, move to the second row. You can move negative there.
Speed is excessive.
Hello?
Reduce speed. Ma, you are fast. You are too fast. Small. Allah. Thank you, ma.
Okay.
Now, fine.
So,
Can you
okay. So have you gotten the explanation for the positive predictive value? Have you gotten the explanation for the positive predictive value?
We're almost
Yes,
about
ma'am.
getting it. Almost there, ma'am.
Yes, ma'am. If you can come back.
Can I proceed?
Please explain it again, ma'am.
Please come back again, ma'am. Please help us, ma'am.
The positive predictive value is the proportion we are trying to interpret now. Proportion of schools with positive classifications that are correctly classified. We are going row-wise. The classification for positive. You have 103 cell A, 33 cell B. Those are the positive classifications that we have. So which cell depicts those that have been truly classified or correctly classified? The cell that depicts the ones that are correctly classified is cell A.
Yes.
That is why it's called true positive.
Okay.
So you get that particular proportion that can be gotten by saying cell A over
Number of observations.
A plus B times 100. And that will give us that 75.74. Is that okay?
It's okay, ma'am.
Yes. Okay. So let's now move to negative predictive value. The negative predictive value is the second row. If you look at that second row, you will see what the model has been able to achieve. So you see for the first one and you see for the second one. And based on my illustrations, cell C is false negative.
Yes.
False negative. And cell D is true negative. Cell D is true negative. And negative predictive value is saying proportion of schools with negative classifications that are correctly classified. Where will you get the one that have correct classification? Which cell will give us that? You can always get that from cell D, because cell D says true negative. So you will get negative predictive value from your cell D. And how do you do the computation? Say D divided by the total for that row. The total for that row, that is a 35 plus 536. And that is 571. So you have 536 divided by 571 times 100%. So negative predictive value is that proportion of schools with negative classifications that have been correctly classified. And that percentage is 93.87. Can I go ahead?
Yes, ma'am.
Can I continue?
Please, I just want you to throw more light on this sensitivity. Now that I'm getting this positive predictive value and negative, so that I can.
Please, I can't hear you. Please, I can't hear you.
I said,
I can't hear you.
Please, whether you can throw more light on sensitivity. On sensitivity.
We have talked about sensitivity.
Please,
we have talked about it. We have said you go column-wise. For sensitivity and specificity, you go column-wise. For sensitivity, you deal with the first column. For specificity, you deal with the second column. For positive predictive value, you deal with the first row. For negative predictive value, you deal with the second row. Do you understand?
Yes, ma'am.
Can I go on?
Yes, ma'am.
Okay.
Dr. Tekwe.
So let's move to the let's move to the next section. The first one there is false positive rate. False positive rate. False positive rate for true. That is for true, not of high quality. That D there is not of high quality. The D is the one of high quality. The true there is not of high quality. False positive rate. If you truly want to understand this thing, please follow this table that I've used to illustrate. Follow this table. If you look at this table, you will see the first cell. cell that contains A, say true positive, cell B, false positive, cell C, false negative, cell D, true negative. Once you understand those, what is the meaning of true positive? What is the meaning of false positive? What is the meaning of false negative? What is the meaning of true negative? There is no problem with interpretation at all. So we are in false positive rate. So the question is, where can we get false positive? That is the first question. Where can we get false positive? From this our table here, where can we get false positive? We can get false positive in cell B. It is straightforward. We can get false positive in cell B. So false positive rate for those that are not of high quality will now be that the value that you have in your cell B, you move column wise, just like we did under sensitivity. Under sensitivity and specificity, we moved column wise. When we went to positive predictive and negative predictive, we moved row wise. So for false positive rate, we move column wise. So identify where you can get false positive. Where can you get it? In cell B. What do you have in cell B? You have 33 in cell B. So the false positive rate now, calculate, when you have to calculate the rate. If you check the note, you see that we have been told that in a normal setting, that cell B and cell C, they should be very, very, very small. What you have there, the percentage that you have there should be very small. Because what is false positive? False positive is saying that something, you are saying that somebody is high quality, the school is high quality. False positive says the school is high quality, when in fact it is low quality. That is false positive. So that is a misleading conclusion. So you shouldn't have too many of that. So the same thing with our C, false negative. False negative. False negative is saying that what is false negative? Because this one is high quality. This thing here is high quality, but it's saying that it is not, whereas it is of high quality. That is what it means. This test is saying it is not of high quality, whereas it is of high quality. So it's false negative. So if you want to get the rate, if you want to get the rate of false positive now, first of all, go to where you can get false positive. You get false positive in cell B, and that is 33. So what is the total for that whole column? It is 569. And when you multiply by 100, you get 5.80. So that's how to calculate the rate for false positive for those that are not of high quality. That's those that have given us misleading conclusion is 5.80. So the next one is false negative. False negative for those that are of high quality. You know, high quality is the one we are calling our own positive. So the ones that are now false negative, you can get it in cell C. Cell C, false negative. False negative is cell C. Again, go to that total, the column total for that place. So that is 35 over 138 times 100. We give you that false negative rate. Is that one clear?
Come again, ma.
False negative rate.
It's clear, ma.
False negative rate. First of all, look for where you can locate false negative. You can get that in cell C. False negative is in cell C. So if you are sure about that, what is the value there? The value there is 35. What is the column total for that place? Is 138. So 35 over 138 times 100. We give us 25.36. That is the false negative rate for true D. The next one is the false positive rate for classified positive. Those that have been classified positive, all those that have been classified as positive, you get them on row 1. They are on row 1. All those that have been classified positive, you get them on row 1. So where will you now get false positive on row 1? You will get false positive on row 1. B. Yes, cell B. Cell B. That is 33. What is the total for that row? 136 times 100. That is 24.26. Is that clear? So
yes, ma'am.
The next one is false negative rate for classified negative. So you go to where you have the negative classifications. That is our row 2. That is our row 2. So we have false negative, then we have true negative.
That's 35.
So you have 35 over 571 times 100.
Excuse me, ma.
Yes.
Excuse me, ma. What is the motive for choosing either 136 column wise or row wise?
Because the row wise is talking about classifications.
Okay, ma.
From our model.
Okay, ma.
The columns, they are the true observations.
Okay.
So that is why for false negative rate, you have that 35 over 571 times 100, and that will give us that 6.13. 6.13. So based on this now, if you have to interpret, most times you talk about sensitivity, you talk about specificity. But if it's a medical research, if it's a medical research, maybe epidemiology or some other stuff, you may be asked to supply more information about the positive predictive value and the negative predictive value and the other ones. But generally speaking, the sensitivity, the specificity, and the overall classification here is 90.38 based on what we have done. And that tells us that this model has been able to correctly classify. This model has been able to correctly classify this 90.38, which is that means that the model has a very good fit. The model has really performed very well because the overall classification rate is 90.38. So that's that about the interpretation under the classification table. Any quick question on that?
Hello, ma.
Hello.
This correctly classified percentage.
Is overall. I'm gonna calculate everything.
Yes. Overall, is there a yardstick for saying, let's say for example, if I get 45%, or if I get 30, if I get 60, what is the threshold line?
The threshold?
Yes. But the overall
doesn't have threshold.
No threshold. No threshold.
What should be considered now? What? It should be the value.
How do you know how do you conclude whether it is high or low?
Either it's high or low. You see something, and anything, our cutoff point for our prediction is 0.5. That 0.5 is like what you are taking as your threshold, your cutoff for the predicted probabilities. So that's like 50%. So you see that what we have there is 90.38, way above that.
Does it mean that if you are at 50%, it will still be classified as correctly classified?
No,
suppose we have that value to be 50%. Suppose we have that value to be 50%.
No, it depends. This is the overall classification, 90.38. It means that our model has been able to classify 90.38% correctly. That is what it means.
So if we have 50%, do we now say it's the overall is also correctly classified, having this value to be 50?
If it is 50%, that means you are saying correctly classified is 50%. That is what you are saying. And if you check your values, you will see that there will be problems with that B and that C. That cell B and that cell C, there will be problems there. That is why we said that if you have that table and you see that there are issues, they shouldn't be very high. That's your cell B and that's your cell C. Your cell B and your cell C, they should not be very, very high.
Okay.
Because once they become very high, that means that you have problem with the overall classification.
Okay, thank you.
You will have a problem with the overall because those ones are the false. You have false positive, you have false negative. They are not true, they are not correct classification. They have been placed in the wrong places. The model has placed those observations in the wrong places. That is what it means. So those that have been correctly placed, those that have been correctly classified, as far as this example is concerned, is 90.38, which is very good. So let's move to the next item. Yes, ma'am.
Did you use any formula for the overall calculation, or you just
No. I didn't. No, that's just the summary from the STATA output.
All right.
Okay. So let's move to receiver operating characteristic curve. Again, this is after you might have gotten your estimate, whether logistic or logic. So this ROC curve, This ROC curve is a graph of sensitivity versus 1 minus specificity. Sensitivity versus 1 minus specificity. As the cutoff, our cutoff C is varied. And what do we need from the curve? We need the area under the curve. The area under the curve tells us about the predictive power of our model. So when you check that area under the curve, the greater the value that you have there, then the greater the predictive power. In another way, if that curve is bound, it's really, you can see that curve sign is really showing that it's curved. As in, the more bound the curve, then the more the predictive power. So we get the predictive power by looking at the area under the curve. We get the predictive power by looking at the area under the curve. So we are still using the same data set. So just that means that we just move from statistics. We move from statistics to binary outcomes, from binary outcomes to post estimation, from post estimation to ROC curve after logistic / logic and so on and so forth. So from statistics to binary outcome, from binary outcome to post estimation, from post estimation to ROC curve after logistic. So if you click that, you will see that window, LROC, compute area under ROC curve, and graph the curve. Compute area under ROC curve and graph the curve. So you see under ROC in the main now, the first one is main. So under main, you see ROC curve. Then the first bullet there, you check it, that's compute area and graph curve for estimation sample. So you click submit. So you can see the graph. You can see sensitivity versus 1 minus specificity. And under that, beneath the graph, you see area under ROC curve. Area under ROC curve is 0.9492. 0.9492. So based on this now, what do we conclude? We conclude that our model has a very good predictive power. A very good predictive power, because you can see that area is 0.9492, very high. Any question on that? Okay, so you know that this is post estimation, which means that we must have estimated before coming to this LROC. Okay, so if we now have models that are different from the last fitted model, if you have a model that is different from the last fitted model, as in you have not done the estimation. This is an example here from slide 17. Models other than the last fitted model. So consider the following logistic model of low birth weight. This is the equation. This is probability low birth weight is equal to 1. That is what has been predicted. You can see the coefficients. The coefficients for age, they are that of LWT, that of black, that of smoke, that of PTL, that of HT, that of UI, and the constant. You have that model. So basically what we are saying is that we know the coefficients, and then we know those variables. We know the variables. We know them. We know we have age, LWT, black, smoke, PTL, HT, and then we can access them. So what do we now do? So let us copy this link, slide 18. Copy that link and paste into the STATA a command window. Have you been able to do that? Have you been able to paste that link into the STATA command window?
Yeah.
Which link, ma?
Yes.
Which link?
Go to slide 18. Slide 18 in our lecture notes.
I'm on slide 18.
Use HTTPS, that link, the first one. Copy it up to clear and paste it in the command window. Make sure you are online. Paste it. Have you been able to do that?
Yes, ma'am.
Okay, thank you. So now that we have that, let's now go to the next line in that slide 18. Copy that next line. That next line is saying matrix input. You know, we input all this manually. We have done that before. How to input? You input that this B here is talking about those coefficients. The coefficients that we considered in the previous slide. The coefficients here, minus 0.02, minus 0.01, 1.3, 1.1, 0.5, 1.8, 0.8, and 0.5. So you can see they are here. Those are the coefficients. So let us just copy that command. Matrix input and paste into the command window. Enter. Have you done that?
Yes. Yes.
Okay, thank you. The next line, let us copy that one too. That one is matrix column names. We're talking about those variable names now. You can see B. The first one is for age. That one is for age. Next one is LWT. Next one is black. Next one is smoke. Next one is PTL. Next one is HT. Next one is UI. Then the last one is constant. The constant. So let's copy it and then let's paste into the command window. So if we paste into the command window now, we will now move from our menu statistics to binary outcomes, then to post estimation, then to ROC curve. Then that window comes out again. Then you see the main ROC curve. Retain that first one, compute area and graph curve for estimation sample. You retain that. If you don't want the graph to show, you say suppress that, but we want to see the graph. So let's now move to the fourth one, advanced. You see advanced, main, if stroke in, wait, advanced. Let's now go to advanced. Advanced. Immediately you click that advanced, you will see dependent variable. Check that box beside the dependent variable. If you check our model, you see we say probability low is equal to 1. So our dependent variable is low. Based on that equation, our dependent variable is low. And then you see vector containing coefficients for the model. It's already there. Based on what we have imputed. It's already there. You can see B bracket 1,8. There are 8. You can see 1, 2, 3, 4, 5, 6, 7, 8. Minus 0.02, minus 0.01, 1.3, 1.1, 0.5, 1.8, 0.8, 0.5. You can see that's the row vector. So the coefficients, they are there. So specify your dependent variable that is low. The vector containing coefficient for the model is already there. Just click submit. If you click submit, you see the graph. The graph has come up. And what do we need? We need area.
I didn't get it, man. I didn't get it. It's bringing out the advanced tab vector containing coefficient for the model.
It's bringing what?
Advanced tab vector containing coefficient for the model must be filled in.
Under your advanced, did you see the dependent variable?
Yes, ma. I choose low.
Okay, after that.
Ma, the vector here.
After
that, I try to submit, but it's bringing out another.
Under the vector containing coefficient, were you able to see B 1,8?
No, ma.
No, ma, not at all, ma.
No.
Okay, close the window that you had before. You know we have worked on LROC before. You know we have worked on LROC before.
Yes, ma.
Yes,
I should close that window.
Yes, close that window and go back to statistics to navigate back that LROC again.
Okay, ma.
Please do that. Have you been able to get it?
Okay, ma.
Yes, ma. Yes, ma. Yes, ma.
Yes, ma'am.
Okay, thank you very much. So now if you submit, you will see
Okay,
the
ma.
graph.
Yes.
You will see the graph. And then you can also see the command. That is L rock low, comma beta B. L rock low, comma beta B. And the area under the curve for this one is 0.7275. 0.7275. So you can still conclude that it has good predictive power. It's more than 0.5 now. It's close to 1. It has good predictive power. 0.7275. So if you want to suppress the graph, you just go back to main. Just go back to main and check suppress graph. Check that box beside suppress graph. Once you check that box, you see that it will give us the results. It will give us the results. 0.7275, but the graph will not be displayed. You can see the command. Say L rock low, comma, no graph, beta B. L rock low, comma, no graph, beta B. So that's that about the ROC curve. ROC curve for predictive power. Any question on that? Can I proceed? Can I proceed?
Go on. Yes, ma'am.
Yes, ma'am.
Okay, thank you. So let's now move to sensitivity stroke specificity plot. Sensitivity stroke specificity plot. So this particular plot gives us the graph of sensitivity and specificity. And the graph is equivalent to our STATA classification under our classification table. If we vary our C from 0 to 1, you know, we can have different cutoff. We can have different cutoff, even though we use 0.5 for our cutoff, but we can have different cutoff. So if we vary our C from 0 to 1, we can have that different sensitivity and different specificity. So again, it's both estimation. We need to first of all do estimation first before we get to that particular section. So let's clear. Let's go to slide 22. Slide 22. Slide 22. You see that second line there? Second line, copy that second line. Copy it and paste into command window. Copy that second line and paste into the command window. Copy that second line and paste into the command window. Have you done that? Have you done that?
Yes, ma'am. We've done that.
Okay.
Yes, ma'am.
The next one is to copy the command. Copy the next command and paste into the window, command window. Logistic, low, age, I race. You have I dot race because that race is categorical. If you check the data set, if you look at that race, you see black is 2, other is 3, white is 1. You see, it's categorical. Even smoke is categorical, but it's just 0 and 1. It's just 0 and so definitely we will still be dealing with the one that is 1 as a default. That is smoker. The other one is non-smoker is 0, smoker is 1. So if you don't put that one if you don't put that I dot, it will still work out well because it's just 0 and 1. But this categorical, if you want your results, you'll be able to talk about that of black, that of others. Then you put that I dot just to be able to bring out those ones. So that's what we have there. Okay. So let us run that. So we have our output now. We have our output. So we want to get our graph. So we go to statistics. Go to statistics, binary outcomes, post estimation, sensitivity stroke specificity plot. Binary outcome, post estimation, sensitivity stroke specificity plot. So when you click that, you see that window coming up. L-sense, graph sensitivity and specificity versus probability cutoff. Graph sensitivity and specificity versus probability cutoff. Are you there? Are you there? Are you there?
Yes,
Yes,
ma'am.
ma'am.
Okay, thank you. So under main, you see graph sensitivity and specificity versus probability cutoff for the first one, estimation sample. So we leave it like that and we click submit. We click submit. Once we submit, you see the graph. You can see the graph. The blue one is sensitivity, and the red one is a specificity. So you can see the probability cutoff. For instance, if we look at that probability cutoff 0.50 down on the x-axis, if you move up to the blue line, you'll see that blue line is sensitivity. If you read it, that's 0.25 sensitivity. Sensitivity is about 25%. It's about 25%. Again, if you now look from that 0.5 again up to where you have, you look at it again for specificity. For specificity, if you trace it, you see it for specificity, it's more than 75%. It's more than 75%.
Excuse me, can people switch off their mic? It is so noisy.
It's not clear, ma'am.
We have on the y-axis sensitivity / specificity. On the x-axis, we have probability cutoff. We are told that we move from 0 to 1 for our probability cutoff. And if we look at the one that we have been using probability cutoff of 0.5. We have been using probability cutoff of 0.5. So if we want to, this particular graph is like the graph under our classification table. Under classification table, we have results for sensitivity. We also have results for specificity. We also have some other results. But this graph will show us sensitivity and specificity. So if we now look, for instance, let's say our C is now 0.5. Look at that 0.5. Check 0.5 on the blue line. The blue line is the sensitivity. The blue line is sensitivity. Check it. Try to read it. What does it give us? Something like 0.25, right? It's giving us something like 0.25. If you look at the same 0.50 for specificity, that is the red one, specificity, you will see that this up, you see up, just trace that your 0.5, trace it, it's up, it's more than 0.75, it's up for specificity, if you read it. If you look at the intersection here, that is where specificity and sensitivity, that is where they have intersected. That is more than 0.25. The cutoff there is more than 0.25, maybe around 0.2 something, maybe 0.28 or 0.2 something. It's more than 0.25. If you see that, you will see that that is where they intersected. And that particular value is more than 50%. It's more than that 50%. It's more than 50%. Where sensitivity
You mean,
and
excuse me, ma. Excuse me.
Yes?
You mean at the point where they intercepted is more than the 50%?
On the y-axis.
Yes, if you look
on
at
the y-axis.
On the y-axis, read it from the y-axis. If you read from the y-axis, you see that that point where they intersected is more than 50% now. Or is it my eyes?
Continue, ma. I
Can you see
understand.
that?
Yes, ma.
Okay. So if you vary that C, you get different sensitivity and specificity results. So this is just a graphical illustration of what we did under the classification table especially for sensitivity and specificity. So that's that. So the other aspect of the lecture note says models other than the last fitted model. Models other than the last fitted model. That's slide 25. Slide 24. Models other than the last fitted model. We first of all fitted the model before we proceeded to the graph. Okay, so if it is model other than that fitted model, again, if we have this model, probability of low is equal to 1 is equal to this. We have this equation. Again, minus 0.02h and so on and so forth. That is the model. And we want to illustrate that just like we did the other time for L-rock. We are now that L-sense. Just like we did. Let us copy this link, this command here. Let's copy this link. And let's paste it into the command window. Paste that link into the command window. I hope you have done that. So after that, let us copy again. Okay, you have not done that. Make sure you are online.
Yes, ma'am.
Okay. Copy the next line. Copy the next line and paste into the command window. Copy the next line and paste into the command window. That next line talks about the coefficient from the stated model, talks about the coefficient. Have you been able to do that? So next, copy matrix column names B, copy matrix column names B, and so on and so forth into the command window. Copy and then paste it in the command window. Copy and paste in the command window. You press enter. Have you done that? So if you have done that, we now move from statistics to binary outcomes, to post estimation, to sensitivity stroke specificity. You move from statistics to binary outcomes, to post estimation, to sensitivity stroke specificity plot. So you retain the first one, that's under main, estimation sample. Then you now move to advanced. Once you click that advanced, you see that vector containing coefficient for the model is already highlighted, that there are 8.
Yes.
8, you have 8 there, 8 coefficients. So again, our dependent variable is low. So specify that, select low as your dependent variable. And then submit. So if you submit, you see the graph of sensitivity and specificity. And the x-axis, you have the probability cutoff. So if you look at our 0.50, for the probability cutoff, for the blue one, sensitivity, for the blue one, if you trace it, sensitivity, you can see, if you trace it, it's more than 0.50. It's more than 0.50. The same cutoff, if you check it for your specificity, you see that it's higher. It's higher than that sensitivity. It's higher. It's very close to 0.75. It's very close to 0.75. Not exactly on 0.75. That line is not exactly on 0.75. It's where it's crossed. It's not exactly on 0.75, but it's very close to. It's very close. And you see the intersection. Between the sensitivity and the specificity. You see the intersection here. The intersection is also very close to 0.50. So we have been able to be able to plot our graph even for models that have not been fitted. We are able to do that because we have the coefficient, we know the coefficient, and we have the information about those variables. We have information about them. So based on that, that has helped us to be able to get the graph of the sensitivity and the specificity plot. And you can see the command L sense low, beta B. Any question on that? Any question? Okay. So if there are no questions, so that is the end of the training. There are other commands, but I think these are of special interest to logistic regression. So basically, we have come to the end of the STATA training. Thank you very much for your attention.